All right, so welcome everyone to GlugNet. My name is Joe Kunk. I am the program director and a longtime board member. I want to let everyone know that this meeting is being recorded and will be available on YouTube. Sam Nasser was gracious and generous enough to do that for us. Feels like a little bit of a reunion tonight. I've known Sam for many, many years. I've also known Michael for many years. And the rest of you guys are all my hangout peeps for GlugNet. So nice to feel like there's a reunion. Unfortunately, it can't be in physically in one location, but at least we can do it virtually. So glad to see everybody here. If you're watching this on the recording, welcome to you as well. It'll be a great session. I know Michael very well. I know it will be. And that's all I wanted to say. Over to Steve.
All right, thank you, Joe. For those that don't know me, my name is Stephen Ball. I am the event coordinator at GlugNet. Immediately following the presentation, we will have a survey to give Michael some feedback on his presentation. As well, we will be giving away one JetBrains license. To enter that, you need to fill out the survey and give your name and email address. So that link will be distributed for the live attendees once we reach the end of the presentation. And speaking tonight is Michael Perry, who will be talking to us on the topic of ACID 2.0, better APIs in messaging. So without further ado, take it away, Michael.
Thank you very much. Let me get the screen share working. It looks like I might have to. This is the first time that I've got this app working on this machine. There we go. So I need to give it permission to do that. Okay. Oh, it looks like it's asking me to restart before I can share my screen. All right, so I will hop off and join in just a second.
Okay, thanks.
Anyone else having a beverage?
Oh, that's a nice one.
Yeah, M43. This is like what I get at the the bar after a lot of times. So. Very nice, Stephen. It's a big mug.
Isn't that from Williamson?
Hmm?
Don't they brew that in Williamson?
Yeah, I think so. That sounds right to me.
Old Nation
Yep,
Brewing.
Yep.
All right.
Old Nation.
There we go. Okay. Yeah. So thank you so much for the invitation and for coming out to spend some time with me. Yeah, I definitely want this to be an interactive conversation. So please, if you've got anything to to say, any clarifications, any questions, come off mute. Let's talk about this stuff. What we are talking about is ACID 2.0. This is a set of principles that will help us to create better APIs, better messages. All of us are building distributed systems of one sort or another. We're building web applications, or we're building mobile applications. Maybe we're building microservices. So these principles are going to help us to build those systems quite a bit better than we could in the past. So I'm Michael L. Perry. I work for a company called Improving, based out of Dallas, down here in Texas. So thank you so much for inviting me to come visit with you virtually. To start off, I'd like to compare ACID 2.0 with ACID, what we'll call 1.0, the ACID properties of a transaction. So this might be review for you. If this is brand new, then that's awesome too. Get a little bit of bonus today, but the ACID properties are things that a database promises to your application. So they're things like atomic, that if you begin a transaction, if you roll it back, no changes will be applied. But if you commit it, then all the changes will be applied. So it's an all or nothing kind of a promise. We've got consistent. That means that any guarantees that your application makes any invariants, things that aren't supposed to change, things that are always supposed to be true, will be upheld. One example of that is if you're building a financial system, a general ledger. One of the invariants is going to be that money is never created or destroyed, that the credits and the debits balance. That would be an invariant. So an ACID transaction helps you to guarantee your invariance and make sure that your data is consistent. This also covers things like foreign keys, that those refer to rows in the database, uniqueness constraints, that those things are truly unique. So that's all covered under the consistency guarantee. Then isolated. You might not be the only application using that database at that time, or you might not, there might be several users using your application at any given time. You might have lots of threads going on. If you've got multiple transactions that are going in parallel, then they're not going to see the changes that are happening in the other transactions. They'll be isolated from one another. And then finally, durable. That's probably the most important one. Basically, when you commit, stuff is saved. Your changes are persisted. It would be very difficult to build an application without the durability guarantee. You save something to the database, come back later and try to read, and it's not there. I mean, that's just the application behaving insane. It's going to look like it's broken. In fact, you might argue that it would be very difficult to build an application if any of these was violated. So these are promises that the database makes to your application in order to make it look to your application like there's only one thing happening, and you can rely upon that one thing. So these ACID properties, they're upheld by several different kinds of databases, have been for quite some time, and for the longest time that's been sufficient. That's just the way that applications and databases work and how they talk to each other. But more recently, we are building distributed systems where we don't just have a single database and several different clients trying to use it in parallel. Instead, we've got multiple databases, and they're spread out across geographies, and they're maintained by by different parts of the organization, and they might have different schemas on them altogether. So these are these databases individually uphold the ACID properties, but what we want out of a distributed system is to take those ACID properties and provide them across multiple databases. What if you have to put a payment into one system and then reserve inventory in another system? Well, you want to make sure that you don't have the inventory reserved if it's not paid for, or you don't take payment if you don't have the item in inventory. So you create these distributed transactions that span multiple databases. And so you have to get these databases to cooperate and both provide all four of these properties to the application. And that's not an easy problem. It's been solved. There are systems you could use to get this. And one of those systems was the Distributed Transaction Coordinator created by Microsoft. And one of the members on that team was a guy by the name of Pat Helland. Now, he's a really smart guy, and he along with the rest of the team, came up with ways to solve this really hard problem of getting distributed transactions to work. And so in 2009, he wrote a math paper about it. He described how you can build something as strong and as reliable as the promises of ACID transactions on top of something as unreliable and transient as a network connection. And so yeah, sometimes network connections get dropped, sometimes messages get lost. And so you have to get to these different machines to coordinate with one another in order to figure out how to uphold these 4 promises. And so this diagram here, this is actually what happens among 3 replicas of a database in order for those replicas to uphold the ACID properties. And yeah, you can see there's a lot of chatter going on. They have to do a lot of coordination in order to make that work. But hey, in this math paper, he shows this works. This is how you can do it. And then about halfway through the paper, he decides to kind of let you in on a little secret that maybe your applications don't need those 4 ACID properties. That maybe if you wrote your application in a different way, you wouldn't need distributed transactions. And so he laid out the properties that your application needs to provide in order to not require those promises from the database. And he called those properties ACID 2.0. Now, the ACID 2.0 properties, they have the familiar acronym, but they mean very different things. These are properties that your application promises, not that the database promises. And if your application follows these 4 rules, then you require a lot less of your database. And then you don't need to build distributed transactions on the quicksand of fallible network. So these 4 properties are the associative property. You might recognize this from algebra, where you can put your parentheses anywhere inside of a, like for example, an addition, so you can add things in different groups, and you'll always come up with the same answer. So some operations like addition are associative. Subtraction's not, division's not, but addition is. You've got the commutative property. Also from algebra, you can add numbers in any order, and you'll get the same result. Not true for division, not true for subtraction, not true for exponentiation, but some operations are commutative. Then you've got the idempotent property. Yeah, even though this might not be familiar to you, it wasn't taught in my algebra class, it is actually a term from mathematics. And it just means that if you were to apply the same operation to a value twice, you would still end up with the same result. And then finally, there's the distributed property, which is kind of an interesting name. Aren't we building distributed systems? Don't we want to make sure our systems are distributed? Well, of course, but the promise that your application has to make is that no matter where you perform your operation, you'll end up with the same result. So no matter how you group things, same result. No matter how you order them, same result. No matter how many times you do them, same result. And no matter where they happen, same result. If your application meets those 4 criteria, then it is ACID 2.0. And then, Pat Helen says, you don't need quite so many guarantees from your database. So let's kind of walk through these and see how that all works. We can kind of boil it down to the 2 hard problems of distributed systems. Number 2, exactly once delivery. Number 1, guaranteed order messages. And number 2, exactly once delivery. And just like any joke, this is absolutely true in that those are the real hard problems in a distributed system, is to guarantee that your message is only going to be delivered once, and it's going to be delivered in the same order relative to other messages. And if you stop and think about the problem, you can kind of see why that's true. If you were to guarantee that this machine sending messages to that machine, everything happened exactly in the same order that it was sent and wasn't repeated, then basically you're guaranteeing that you can just serialize this sequence of messages, and you'll end up delivering exactly that stream. But in a network, you can have drop packets. Things might get lost. You might have to retry because you don't know if something made it to the other side. You can have something dropped on the way back. So you're not sure if it was received, and so you have to try again. There are lots of systems that go to extra length in order to make sure that these two guarantees are upheld. Like, for example, Kafka. Kafka has a data store of all of the events that have occurred. So if you go to that data store and you say, well, this is my bookmark I've seen up to this point, it's not going to give you the old events. It'll start from that point and just go forward. It will give you the events as they appear in that stream and not out of order. So Kafka takes on that responsibility at the cost of having to have that data store of the stream of events. Other systems might just have a queue that as soon as you pop something off the queue, then it's no longer there. Well, of course, you have to tell it that you succeeded in processing that message. Otherwise, you might lose the message. So you pop a message off the queue and something goes wrong. Maybe you've processed it, but you weren't able to get back and say, I've handled it. So next time you come back and you grab that message, it'll be the same message. It's really hard to guarantee that it's not delivered more than once. So these are some pretty hard problems, and they're kind of related to the distributed transaction problems. And as it happens, the ACID 2.0 properties mean that we don't have to worry about these problems. So let's take the exactly once delivery. If our system is idempotent, then we don't have to worry about exactly once delivery. Let's take a look at an HTTP resource. We can get people42, and we've got the value name Bob. Okay, so if I were to put to people42 the new value of name Robert, now the value of that resource is name Robert. So what if I put to people42 again the same value, name Robert? Well, that's not really a change. The value is still name Robert. So I'm doing an operation more than once, and I'm getting the same result. So you might recognize that put is one of the verbs in HTTP that's guaranteed to be idempotent. It's a guarantee that it's going to give you the same result if you were to repeat the verb. There's a few others. Patch is another one. Delete is another one. But post, not idempotent, because post is intended to create a resource. So you post to a collection, and then the new resource comes back. So if you were to try to do that again, you would get another resource. You would duplicate the result rather than making sure that it was the same. So some verbs are idempotent, some are not. But if you build your system out of idempotent verbs, then you don't have to worry about exactly once delivery. Okay, seems like a good solution. But there was another hard problem, right? Not just exactly once delivery, but also guaranteed order. So for that, let's take a look at commutative operations. So let's suppose that I'm building a game where I can find a word in like a bottle grid. I score the word and I say, okay, I found that word, score 3 points. Now I've got a total of 3. I found a different word. Okay, score 5 points. Now I've got a total of 8. What if I sent those scores to the server and they were received out of order? Well, then I would score 5 points and then 3 points. I would still have a total of 8 when I'm done. So I'm taking advantage of the fact that addition is commutative. And so now my operation of scoring points in a game is commutative. So that seems to be great. If I build my applications such that all of my operations are commutative, then I don't have to worry about guaranteed order or delivery. Okay, so it looks like we're on a good path. The problem is some operations are idempotent but not commutative. So let's go back to the HTTP put, for example. So again, we've got a resource. The current value is name Bob. If I were to put to people42 name Robert, I've just changed the value to name Robert. But now I put to people42 name Larry. What's the current value of the resource? It's name Larry. Now, what would happen if I got those things out of order? I would get a different final result. So that means HTTP put, while it's idempotent, and that's good, it is not commutative. So that means it's not enough. That means that just making an API out of your idempotent verbs, it still leaves you open to messages arriving out of order because they're not commutative. Okay. So yeah, we need to look out for that. The opposite problem can happen too. You can have operations that are commutative but not idempotent. So let's take a look at our Boggle game. So I've scored 3 points. I've got a total of 3. Scored 5 points. Got a total of 8. What if I receive the score of 5 points a second time? If my operation were idempotent, I would still end up with the same result. I would still end up with the 8 points. But just using addition, I end up with 13 points, which might be okay for me, but certainly wouldn't be very good for my opponent. And so people would not really have a lot of fun playing that game. So you want to make sure that the message handler is not just commutative, but also idempotent. So if you're commutative and you're idempotent together, then you've taken care of the 2 hard problems in distributed systems. But we're not quite done. That's only 2 of the ACID 2.0 properties. Let's take a look at the third one, the associative property. So let's suppose that you're building an ordering system, and as you receive orders, you go ahead and process those orders against your database, and you're handling things just fine. And then you've got a reporting database. So your boss wants to be able to run a report every night in order to see how many orders were processed that day. So that means that you're going to take all of these orders and you're going to batch them together. And you're going to send one day's batch off to the reporting database. It's going to crunch those numbers, give you some output that then you can report against, get that day's report, create another batch, send that day's transactions in, get a different report. So that's working pretty well until your boss comes to you and says, okay, I really value this information and I need it more frequently. So I'm not going to ask you for real-time reporting. Let's not go crazy here. But once an hour, let's try that. So you should be able to take these batches and then now batch them in a different way. And the result should still be the same. So it should be just fine if you were to batch 24 hours individually, as opposed to doing a full day's batch. And if you end up with a different result, if your boss runs the report and things end up differently because of the change, then he's not really going to trust the system. In fact, he's going to question, was the report right in the first place? So we definitely want to make sure that our batch operations are associative, that no matter how we batch them, we're going to get the same result. So far that covers 3 of the ACID 2.0 properties, and those 3 happen to come from a field of mathematics that spoiler alert if you haven't seen me before, I am a math geek, and this is my opportunity right now to just introduce you to an awesome new concept. So mathematicians come up with crazy words to mean things that, where did that come from? And mathematicians have decided that if an operation is idempotent, commutative, and associative, then that operation forms a semilattice. Well, where did that word come from? It's kind of strange. Well, let me see if I can give you a visual that helps you to understand what that word means. So let's take the idempotent property. So we saw that if you were to perform the same operation twice, you would get the same result. That's what idempotent is defined to be. Well, here I've got it written in something that looks a little bit different, but it's actually, that equation means the same thing. If I've got the value x, and then I apply some operation with x onto that value, I stay at x. I don't move anywhere else. So you can think of a value like x as being a state of your system, a place that it's currently in. And then applying an operation, here I'm just using the hat operator to represent whatever operation I'm talking about. Could be plus, could be divide, could be square root. Well, square root's not a binary operation, but you get the idea. I apply any operation, and if it has this property that whatever value x at x hat x is equal to x, then that means it's idempotent. So yeah, certainly not true for addition. 3 plus 3 is 6, so addition is not idempotent. But you might think max. Take the maximum of two numbers. Max of a number with itself is going to be that number. Okay, max is idempotent. So you've got this starting value x, and you can apply any other value in the number system to it, and that will get you into this new space. So that will move you from x somewhere else, and so we'll visualize that as a cone, kind of leading out from x. If you're a physics nerd, then you might be familiar with the idea of a light cone. That is, when an event occurs, think of a sphere just expanding at the speed of light from that point in space and time. And anything inside of that sphere could be affected by the event itself, but anything outside couldn't. Light wouldn't have enough time to reach it. So that is like the future light cone of that event. So here, just kind of visualizing that as some operation can happen, and these are the future states that x could evolve into. To help kind of bring that down to earth a little bit, if every operation that you performed, like maybe you've got a hit counter on your website, every operation you perform on that hit counter can only increase it. So the future state is all the numbers greater than the current value. So that cone is really just the set of all numbers bigger than x, or equal to, because you could stay right where you are if you don't click it. But click it any number of times, you're going to move into that future cone. So that's what I'm trying to visualize here. So let's bring in y. Let's say that I'm going to take x and I'm going to combine it with y using this hat operator. So that means I'm going to move into a value that's in the future of x. I've applied the operator to x, but I'm also going to move into the future of y. So that means that I meet at this intersection x hat y. Now the commutative property tells me that if I started at x and applied y, I'll end up at the same place as if I started at y and applied x. It doesn't matter which order I did those in, I'm going to end up at the same place. And so now you can see that there's a new future cone that is created from that point, and it includes the intersection, the things that are in the future of x and in the future of y. And that's how the commutative property kind of looks to this, this mathematical operation. So now let's take a look at the associative property. And you can see here we're combining three things. So the associative property just algebraically is saying that I can take y hat z first and then apply that to x, or I can take x hat y first and then apply z, and I'll get the same answer either way. So visualizing that, you can see, well, if I start at z, then combining that with y, I'll end up at y hat z. Starting at x, I'll end up with x hat y. But no matter which one of those I use, when I combine all three of them, I'll end up at x hat y hat z. The intersection of those three is that particular point. And so that creates a new future from that point forward. So that is kind of how I visualize what it means for an operation to be idempotent, commutative, and associative. You're always moving into this future cone, and you're moving into the intersection, the very point of that of the intersection there, so that little vertex. And so now you can start to see why mathematicians call this a semi-lattice. I mean, if you go out in your backyard and you take a look at your rose trellis, you might see that it's growing up this this structure that's got a whole bunch of diamonds on it. That's a lattice structure. So a lattice is a bunch of objects that are closed at the top and the bottom. They have a point at the top and the bottom. A semi-lattice is closed at the bottom but open at the top. It could actually be open at the top and close to the top and open at the bottom. We're looking at the ones that are closed at the bottom. By the way, if you really want to get into this, this one is called a meet semi-lattice, and the one that's closed to the top is called a join semi-lattice. But that's maybe a little bit more than you were after. This is probably already more than you're after. But this is what I love. I love this this math stuff. So let's bring it back down a little bit closer to Earth. And so far we've been talking about just operations in general. If an operation has these three properties, then it is a semi-lattice. Well, we already know addition's not a semi-lattice because it's not idempotent. We looked at max. Okay, max is idempotent. Max is commutative. Hey, max is associative. All right, max. That looks like a good candidate for a semi-lattice. So you can see that taking the maximum of things gets you to that point furthest in the future of all the things. That's kind of what max means. So let's try to think of what would be something that would be like max. It would be a semi-lattice, but it would be a bit more useful. And so one of my favorite examples is set union. The set union operation is idempotent, commutative, and associative. It's a semi-lattice. So if I were to look at idempotency, that means if I union a set with itself, I get that same set. For example, I've got the set car. I union it with the set car. The result is the set car. Why isn't it the set containing two cars? That's because sets don't count things. Sets don't have multiple copies of a thing. They just contain things. So so the car is either in or it's out. So you end up with a set that just contains car. So that means that that set union is idempotent. That's going to be true no matter what set you throw into that. So what about commutative? Well, if I were to take the set car bicycle, I'm sorry, the set car and union the set bicycle, I would end up with the set car bicycle. If I were to do that in the opposite order, bicycle car, I would still end up with the set car bicycle. Oh, wait a minute, why not the set bicycle car? Well, that's because sets don't order things. They only contain things. So you can't tell which one was put into the set first. It's just in or it's out. So that means if I were to write the set bicycle car, that means the same thing. So we end up with the same set. Sets are idempotent. Set union is idempotent and commutative. So what about associative? So I start with just X, just the set car, and then I union that with Y union Z, so the set bicycle train. And I'll end up with car, bicycle, train. What if I were to take those in the opposite order? What if I were to start with car, bicycle, and then union the set train? I would still end up with car, bicycle, train. So it doesn't matter how I group things. It doesn't matter how I order things. It doesn't matter how many times I try to apply set union. I always end up with the same answer. So that means if I could build my data structures based only on set unions, then I would be building a semi-lattice in the software, and that means that it would tolerate out-of-order messages, it would tolerate duplicate messages, and I guarantee that if I group things in different ways, I'll still end up with the same result. So pretty powerful stuff. But I'm still missing one more property. So ACID 2.0, I've got the A, the C, the I. Now, how about that D? Remember what that stood for? That was the distributed property. So distributed means that no matter which database I apply this change to, I'm going to get the same result, which replica or which instance of the microservice or which whatever you like. So that seems like a gimme, right? Our applications are all deterministic, right? We don't generate random numbers most of the time from our apps. So no matter what you do or where you do it, you're going to get the same result. But that's not quite accurate. Take, for example, a database that has an auto-incrementing ID. One database might have 17 rows in it, and the other one might have 316. So you do an insert on one, you'll get back row 18. And the other one, you'll get back 317. So you're going to get a different ID based on where you apply that transaction, that insert operation. And that is going to be important if you now want to take that ID and use that as the identity of the thing you just inserted, because now you have to know where you came from. So if I get back ID 317 from this database, I can't turn around and ask this one for record number 317. It's going to be a different record if it exists at all. So the location matters in that case. The identity of things is dependent upon their location. And so inserts, when you've got auto-incrementing IDs, are not distributed. And that can that can be visible, that can come back to bite you. So you really do have to have all four of these properties. You have to be associative, commutative, idempotent, and distributed in order for your application to behave reliably and not have to take such strong guarantees from the database. So at this point, I'm going to kind of transition into some concrete examples, but if we need any clarification before I do, then please unmute and speak up.
I just want to say thanks. I think that was really great examples. It was nice to see that broken down.
Okay, cool. I love it. Yeah, if I didn't enjoy software so much, I'd be a math teacher. In fact, maybe when I retire, I will be.
I'd probably like your math stuff.
Cool. So let's look at some very concrete examples of how we might apply these properties. So we're building a mobile application, and in this mobile application, we are keeping track of people. So we're some kind of contact list. So the user of the mobile app creates a brand new person, and then it needs to make a call to the back end in order to save that data. So it posts to the /people API, and then it waits. Meanwhile, the web application, okay, I just received a post for /people. That means I have to create something in the database, so I'm going to do an insert. So start my insert, and it waits. Now the database does its insert, it allocates the ID, and then the application needs to get that ID, so it uses @identity, and now it knows, okay, this was record 42. Okay, great. Now it takes that 42, it sticks it onto the URL, and it throws back a 301 created people/42. And now at that point, the mobile application knows the identity of the person it just created. It couldn't have known that number 42 any sooner. It had to wait until that 201 created came back before now it can take that identity and keep track of it. And the reason that the app is waiting is really that probably the very next thing that the user of the app is going to do has to do with the identity of that person object. They're probably going to start entering a phone number and a name and other properties of that person. Or they might hit the share button and want to send that information to somebody else, in which case we'll need to take that URL and send it off somewhere over sharing. But the application doesn't have the identity until we get back the 201 created. So it pretty much just has to wait. Meanwhile, you've got this web server. It's just taking these HTTP requests, doing the insert. It can't give back the response until it the transaction completes, and we can do add identity and figure out what the ID is. So it's stuck waiting. So you've got all of these different clients and all of these different web servers all waiting on this one database, because the database is responsible for coming up with the identities of all your objects. So this system doesn't really scale all that well. It's not really a distributed system in the sense that that we want it to be. Sure, it's distributed in that we've got lots of different nodes running around in people's hands and in their pockets, but and then we've got lots of different servers all in a cluster, but they're all kind of bottlenecked on this one database. And the disturbing thing to me is if you open up Visual Studio and just file new project and you create a web application, use the template that uses Entity Framework too, bring that in there. This is what you get. You get something that does an insert, takes the ID of the thing just inserted, and uses that as the URL. This is the way that we build applications, and it has this fundamental flaw in it. That means that we have to wait on the database to generate identities for us. So maybe we can fix that. Maybe we can solve this problem. So let's take a look at this from the perspective of the ACID 2.0 properties. So we'll start with the associative. We're just creating one person at a time. We're not really creating groups of people. So we don't really have parentheses in this operation. So we can put associative aside for this particular operation. Commutative. So if I were to create a record for my mom and then create another record for my dad, and then I'll get back to IDs and then I start using them. It doesn't matter which one I happen to get back first. It's just one's for one person, another one's for another person, and then they start to take on meaning. So commutative, sure, we'll give it the commutative property. But what about the other two, idempotent and distributed? That's where we run into some problems. So let's see how our API is not idempotent. Well, we have a clue right there at the beginning. This is using a post. So that means that it's not guaranteed to be idempotent. It's a perfectly valid RESTful API if post is not idempotent. And so we're going to post to /people with name Robert, and the system might give me back people42. If I were to repeat that and post to the same endpoint the same value, I'll get back a different result. More importantly, it's not just that I got back a different ID, it's really that the final state of the system has changed. That whereas with just one request, I ended up with one new object. With a repeat of that request, I ended up with two new objects. So that means that we're not being idempotent. But that's not the only problem. We're also not distributed. So we drew this architecture of lots of different phones in people's pockets, a cluster of web servers, and one database. But let's think through the fallacies of distributed computing. One of those fallacies is that the topology doesn't change. So we drew a topology of lots of phones, a few web servers, and one database. But what if that changes? What if there's a reason for us to have two separate databases. For example, let's suppose that we've got an active standby. So everything's happening to this one database, but then we're log chipping over to this other one. And now we fail over. So now we're doing everything over to this one. Now that one's still there, and the logs are still moving across this this log shipping network here, and maybe this thing crashed, and we have to bring it back up. And now we start to replay those logs a little bit. So now we've got this data coming in here, we've got data coming in from over there, and we say, okay, everything is up to date now. So now whoop, fail back. Oh, wait a minute, we had some things that were happening over here, so we have to ship some logs back this way. You've got two different databases, and you're trying to generate IDs in both of them. And so you're going to have these scenarios where you increment your auto incrementing ID, and you use, okay, I'm 351 here, and then I just inserted 351, and that's coming in on the transaction log. So okay, I have to wait until the transaction log comes in before I can resume. Oh, but what if the machine's down? That's the whole point of having the live backup. Hard problem. Well, if our system is not distributed, well, what that's telling us is that I do the operation on one database, I might get back one result, like people/17, and do that same operation on a different database, I get back a different result, like people 351. And now I can't use those URLs on the other database. They mean different things. They're in completely different ID spaces. So the identity can't move from one location to another. It's stuck to that location. And so that means that it's really difficult to have these systems at some point in the future talk to each other and say, hey, you got people 17? I sure do, but it's a different one than you got, so yeah, that doesn't really help us. And that's fundamentally that this system is not being distributed. So how can we solve the commutative and distributed properties for, the idempotent and distributed properties for this system? Well, let's start with idempotent. If we just replace the the post with a put, now we can take advantage of the idempotent property of the API. So that means that rather than posting to the collection and waiting for the identity to come back, I'm putting my desired ID. I'm putting a resource to what I think the ID should be. So in this case, I'm going to put to people/Bob1945, a resource with name Robert. And so the identity of that resource is people Bob1945. All right, that's good. If I need to repeat that message, post or put to people Bob1945, name Robert, the identity of the resource is still people Bob1945. I haven't duplicated the resource by putting to it twice. So you might think, okay, how am I going to transform posts into puts? That means that I need to come up with some ID on the client in order to do that. But the client doesn't know all of the other numbers that the other clients are generating, so how can it be guaranteed to be unique? Well, you don't use auto-incrementing IDs in this case. There's no way to get the next ID in a distributed system. Instead, you use things like GUIDs. You can use timestamps if you combine them with other things. You can use public keys. I love those. Those are great identifiers that are generated on the client side. Or you can use natural keys. That's probably the best kind of a fallback. But you think through, how can I get my client to generate a unique identifier for the object that is creating? And then you've solved the idempotency problem. Just put to that identifier. But surprise, that means you've also solved the distributed problem. Because now the server's not generating the ID. And so any server that you send it to is going to save that resource with that same ID. And so when they get together and they talk about, do you have Bob 1945? Yes, I do. They are both talking about the same thing. Furthermore, this also solves the original problem that we saw about the client waiting. Oh, goodness. Stay there, Mr. Biscuits. The client waiting on the server to generate the ID. If the client is generating the ID, then that means that it can keep going with its work. It can synchronize in the background. It can just store that in a local queue, and then when things finally settle through, then it's going to have the same ID that it expected. So it doesn't have to wait for the ID to come back. It can continue serving the user. So client-generated ID, change your posts into puts. It solves the idempotent and the distributed properties in one fell swoop. So that would be a great way to design a web API using the ACID 2.0 principles. But there's an even better example. So I'm about to switch into talking about microservices, but if we have any clarifications we want on APIs, then go ahead and unmute. And I will get Mr. Biscuits.
I didn't want to make just sure, because like you could pass an ID with create, but is that just a violation of what the create is on a post? I mean, sorry. Is that like a violation of like something essentially?
As it happens, it's not. So yeah, HTTP does not guarantee that post is idempotent, nor does it guarantee that it's not idempotent. So if you decide to make post idempotent by passing an ID in the body, for example, then you're good.
That like put is supposed to handle for creates or updates, and that's like what we're doing here at least. And so that makes sense. Okay, thanks.
Yep, exactly. So yeah, you could solve that problem by just making the verb more constrained than it's specified to be.
Yeah, because it is really helpful in a lot of scenarios where you're doing anything that's like I always find that caching's hard when you do a lot of things like in the database, or something like that. Same kind of concept here. I think when you create that ID on the client, it makes it a lot easier to not worry about the response from the client. So then like CQRS, that where you're doing a command side and a query and you have eventual consistency. And so the idea of like being able to send in the ID helps you to be able to manage some kind of state locally, if that's how you do it, in order to be able to read that record if you need to read that ID. You don't have to wait to go to the list and find it, So it's so it is a good approach.
Yeah, exactly. Yeah, I love that several different aspects of the industry have come to the same solution, which kind of tells me that there's something to it. There's some fundamental core to it.
And that's why I think this is helpful to hear like a little bit more of like a pattern, an example of how to do these things, and then see how that relates to the things that we're trying to do maybe, and then have a little bit something to be able to go back to other people and saying we really should be using a put here instead of a post, or we should make these things work this way because of ACID 2.0 now, right? I can say that. So it's nice.
Yeah, and being a mathematician, if you can write me a theorem, then I believe you. I'm with you. So yeah, I'm that guy that would be in the room and say, well, okay, but prove it. So okay, QED. Oh, okay, go forth. So so now let's transition to talking about microservices, the great new buzzword. So here I'm going to build out a microservices architecture to fulfill an order, and it starts with my online store. So somebody goes to the online store, they got the web interface, look through the catalog, add things to their cart, all of that good stuff, and then they place the order. So the online store publishes an event to a topic saying the order has been placed. Now, the inventory system is subscribing to that topic, so it sees that the order's been placed, and then it starts to check to see if it's got those items in inventory and do all of its inventory things. Meanwhile, the accounting system is also subscribed to that topic, so it sees the same order placed message, and then it starts to create my my invoice so that it can send it off to the customer and do all of its accounting things. So back at the inventory system, it has found those items in inventory, so it reserved them and then sent an items reserved message to a queue that the logistics system is pulling messages from. And so now the logistics system knows that those items are reserved. It needs to tell some people to go pick those items off the shelf, pack them, get them ready to ship. And meanwhile, the accounting system has seen now this order's been placed, so it created this invoice and now sent this invoice message off to the business portal. The business portal is a place where the person who actually has to pay for what the boss ordered logs in and sees how much we owe. Oh goodness, okay, get out the company check and write the write the payment for that invoice. So they do all that through the business portal, and that payment goes back to the accounting system, and it satisfies that accounts receivable, and so everything is nice and balanced, and money moves, and everybody's happy. And meanwhile, the box has gone onto a truck, and so now the guy in the warehouse is okay. It's been shipped, and here is the shipment record with the bill of lading and the tracking number and all of that information. Send that all to the business portal. So now the person in the back office can log on there, see that these items are on their way, and keep the boss up to date. So all of these messages are flowing through the system, and you've got this thing broken down into these nice little microservices that are each handling one unit of responsibility in order to fulfill an order. And your job is to prove that if these messages arrive out of order, nothing's going to break. If these messages are duplicated, nothing's going to break. If these messages get grouped in any different way, not going to be a problem. And that no matter which replica receives the message, it's going to handle it in the same way. Because you don't just have one instance of the logistics system. No, you have at least 3. You might even scale up to 5 on busy days. You don't just have one business portal. You've got 7 of those out there so that you can receive all these different web requests. So no matter which replica you hit, it's going to give you the same result. How do you prove the ACID 2.0 properties in a distributed system like a microservices architecture, where you've got all these different messages that need to compare with one another? Well, let's go through them one at a time. So we can start with idempotency. So how do we know if a message is idempotent? Well, this one's the easy place to start because you just have to compare it with itself. So if I receive order placed, maybe the message looks like this. So I've got my order ID, I've got my items, and I process that order, I end up in a certain state. If I were to receive that order placed message a second time, I want to guarantee that I end up in the same state, aka nothing changes. So one way that I could do that is I could just keep track of all of the orders that I've received. Okay, let's look at that order ID. Have I already seen it? Yes, I have. Do nothing, just drop the message on the floor. This is a duplicate, ignore it. Well, that's fine unless somebody sends an order placed message with the same order ID, but different order line items. So if that happens, then it matters. It matters very much that I would be dropping this one on the floor, because all of those extra line items wouldn't be added to the order. So when might that happen? Well, think about the online store at the very beginning. what if it had a flaw that that you could hit submit, but before everything worked through, you could hit submit twice. I mean, you've seen lots of different websites, especially back in the 90s, that had this huge message: "Don't click submit twice." That's because they didn't know how to solve this problem of making that submit button idempotent on the web application. So they just left it to the user to not duplicate a message. But if the user does click submit twice, if the web application doesn't know how to handle that, then it might come up with a new order that is different than the other one. And if we're just using the order ID to dedupe these things, then we're dropping that information on the floor. So it's not really that we want, well, I mean, yeah, what we really want is idempotent messages, but the way that we can get them is to enforce that these messages can't change. So instead of idempotent messages, I'm going to say what we're really after is immutable messages. So instead of allowing this third message to happen, what if we just did not allow it to happen? There was absolutely no way that you could write a defect to cause this duplicate message. Wow, that would be quite a guarantee. How can you uphold that guarantee? Well, I happen to have right over here just such a message. So if I take a look at my order, then you can see this is my JSON structure. And so just to make it prettier, I'm going to pop that through JQ so that we can see things a little better. I've got my order ID and I've got my line items. If I do a -C, that gets rid of all of the white space. And then you can imagine if I further put all of the fields in alphabetical order, then what I'm doing is I'm generating a canonical form of this message. Any JSON object that has these fields, exactly these fields, and nothing else, is going to come up with the same string. So that string is unique and canonical to this message. So that means that I can take this and I can run this through OpenSSL, create the digest using SHA-256. And if I take a look at that in binary, then I've got this nasty stuff. Well, I can also take a look at that in base 64. And now, there we go. There's a string. That string is generated from this message, and it's generated from the canonical form of the message. So that means that if anybody tries to send that message, even if it's in a different order, we've taken care of that by taking out all the white space and sorting things alphabetically. We'll come up with that same number. And so that means that I can use that number as the message ID and not the order ID. So I don't care if I've seen 123XYZ before. What I really care about is, have I seen W7V, and I won't read the rest of it to you. Have I seen that before? So generate an ID from the message based entirely on the message, and use that as the identifier for those messages. And now those messages are immutable by their very nature. Why is that? If I were to change the message in any way, add some fields to it, change the value of some fields, and then I would be generating a different ID. It would be a different message. I couldn't, well, unless I could crack a SHA-256 hash, I couldn't generate a new message with the same ID. I couldn't change the message. I couldn't mutate it. So, so this is what I like to use for my message IDs, not something intrinsic to the message itself, not something that was tacked on in some location along the way. No correlation ID somewhere. It's a hash of the message.
Sorry, couldn't order of these though be a problem in this case and stuff? Have you received messages in order?
Yeah, so like for example, the order of the line items?
Well, more like if you receive the messages out of order. Because like you said, like your example was you added line items, but what if you received it somehow in the wrong order where you actually remove line items then. From it.
Yes. That is the commutative property, and we are coming up on that next.
Oh, cool. Okay, sorry.
Yeah. No.
Hey, Michael, this is
Well,
Joe. Another question is your argument is fine as long as SHA-256 never has collisions. So how would you address collisions in this scenario?
Yeah. So so I would say there's two ways to get collisions in a hash. One is accidental, one is on purpose. So the to address the accidental, I actually have worked out some math, and I published that. Of course, I worked out the math. It's me. And I published what is the probability of a hash collision in any particular data set. So it worked out that if you've got a data set of 1 billion records, and you use actually this was based on SHA-1, so that's only 160 bits. If you use SHA-1 to hash those records, then the probability of a collision anywhere within that data set, not just between any two records, but anywhere within the billion records, works out to be 1 in 10 to the 30th or 10 to the 31st. So so a really, really tiny number. I mean, just astronomically tiny. And that's for SHA-1. I mean, if you're really worried about it, then go with SHA-256. So that brings it down even further. Or yeah, heck, why not SHA-512? It's just never going to happen accidentally. Now, then there's deliberate collisions. The SHA family of algorithms was designed to be collision resistant, which means that there's not enough information left in the results for you to find a pattern in what you started with. So so some early hashes didn't have that property. In fact, like things like CRC32, not intended to be a cryptographically strong hash, but CRC32 is trivial to find a hash collision. It wasn't designed to avoid them. So there's a very simple algebraic relationship between the input and the output. But yeah, in the case of the SHA family of algorithms, finding a collision is just really intractable. So yeah, I would say it's certainly not impossible to get a hash collision, but yeah, the likelihood is extremely low. You can bet your career on it. So that is how I like to identify the messages so that the body of the message is immutable. Oh, one other thing. This also happens to solve the distributed property, because no matter which machine you send this message to, it's going to compute the hash in exactly the same way. Hashes are deterministic, and the input to this hash is only the message itself. So it's not auto-incrementing a number, it's not coming up with the GUID. So it's always going to be the same ID. These hashes are distributed. So you got 2 for 1 there. Okay, so that is immutable messages, taking care of idempotency and distributed properties. Now let's take a look at that commutative property. Okay, so here we have to really think through all of the different messages that are happening in the system and compare, what if I receive one before the other? Can these things commute? So order placed. Well, the example that you gave is one order placed doesn't commute with another. What if they updated their order to add some items and you received it out of order? It looks like they removed items from their cart and then submitted a second time. So you gotta account for that. So suppose we come up with a solution there. Well, now you've got with the order placed compared to the items reserved. Can I reserve the items before I place the order? Well, no, that doesn't really make sense. Well, how do I account for things if I do receive them out of order? That's going to be kind of a hard one to figure out. But now what about items reserved versus the invoice? Does it matter if I reserve the items before I invoice or if I invoice before I reserve items? Well, no, I could do either one of those in either order, and that's going to be fine. And so you have to kind of go through pairwise the whole set. And then anytime you add a new message to your system, you got to compare it to everything else that could have come in. And so doing this by hand is just gonna slow you down over time. And this is why systems rot, is that you've got some complexity now. Oh, new feature. Oh, all that complexity. So there's a better way to look at this. Instead of looking at all these messages independently, just look at them like this. Let's take the messages that have to happen before another one, and let's just draw an arrow. So before I can reserve some items, the order has to have been placed. So let's just draw an arrow. Before I can ship the items, I have to have reserved them in inventory. So let's just draw that arrow. Now let's compare items reserved to invoice. Well, they could happen in either order. There's no arrow between them. And you could also see that there's no path following in the direction of the arrows to get from one to the other. So that means that order doesn't matter for those two. The same way with payments and shipments. Order doesn't matter. Now the shipment definitely has to follow order placed. So you're transitive across these arrows. But if you don't have a path from one to the other, order doesn't matter. And when you draw things out this way, you'll find that most of the time, order doesn't matter. So I can ignore the order of operations in most of my messages, but when I can't, I need to know about it. And so it's not just that we're looking for commutative messages, but the way that we get commutative messages is we look for partially ordered messages. So partial order, that's another one of those math terms I'm going to lay on you. That's as compared to total order. So a system is totally ordered if I can, or a number system, for example, is totally ordered if I can pick two numbers and compare them. And I say one is less than the other. So, the integers, totally ordered. 3 is less than 7. Okay. But there are some systems that are partially ordered where I could pick two numbers, compare them, and I can't get an answer. I can't tell which one came before the other. One example, let's take the integers, but this time under the operation of not less than, but is a factor of. Okay, so 3 is a factor of 15, so I can compare those two. I know which one is the factor of the other. It's not that 15 is a factor of 3, 3 is a factor of 15. So they come in that order. And 5 is a factor of 15. Okay, but 3 and 5, when I try to compare them, neither one's a factor of the other. So you can't put them in order in that case. So some systems allow a partial order. They don't require a total order. When you put a bunch of operations in sequence, you are imposing a total order on those operations. But if you allow them to be partially ordered, then you can go ahead and be commutative for those things that don't matter. And you're going to find that that's quite a lot of them. Now, when things do matter, that's when you've got that arrow. That arrow says to me that the one at the head of the arrow is a predecessor. It has to have come first. So the order is placed before the items are reserved. So the other thing that it says to me is that in order to have to make sense of the successor, the one at the tail, in order to make sense of it, I have to know what the predecessor is. So when I reserve items, I'm going to reserve items from the order. So I need to know what that order is in order to do my work. If I'm going to ship things, I need to have that packing list. I need to have the items that were reserved. Without them, I can't do my I can't do my work. In order to make a payment, I need to know how much to pay. That's in the invoice. So the predecessor gives me useful information in order to complete the successor. So if the predecessor has to happen before the successor and it gives me useful information anyway, then why not just embed the predecessors in the successors? So how does this solve the problem? So we've got that order message right there, order ID with the line items, and I've embedded that inside of my invoice. I didn't just simply say invoice ID, pay me 354 or 345, and then order ID 123XYZ. No, I spelled it out. I said, here's the full order. I mean, it helps me in one way in that I don't have to go to my database and look up the order to get the items before I can actually now create the invoice. I've got all the information I need right there in the message. But it helps me in another way. It helps me to be commutative. Because what if this was the first message I received and I hadn't yet received the order? Well, yes, I have. It's right there. There's the order. So I can just simply take the message, take it apart, and process all of its components first. And if I've already got that order, then I'll compute the hash. I'll look it up. Say, oh, I already know about that one. You know, that's fine. Pop the stack. Now I'm back to the invoice, and I can process the invoice. But if I hadn't received that order, here it is. Process it. So embedding your predecessors forces the messages to arrive in order, and it gives you the information that you need anyway. So yeah, it does bloat your messages a little bit, but one thing I found is that this graph here usually doesn't get terribly deep. It gets wide. And so that depth of the graph is telling you how many predecessors are embedded. So that's what's growing the size of your messages. The width, that represents the messages that could happen out of order anyway. That's why I love these graphs. And by the way, this is a directed acyclic graph. If you haven't practiced coding against DAGs, fun problems. Everybody should write a topological sort in their lives at least once. So embed your predecessors. Now, what about if you've got something that is like an order placed where you can change things, and so you want to make sure that that it arrives in the proper order. Do the same thing and make order placed a predecessor of the next order that's placed. So let's suppose that you are working on that web application. You know, people add things to their cart, they hit submit. The very first thing that you do is you create that order placed record. And now, if they add some more stuff to their cart, you take that order placed record and you embed it within. This is the prior one. And now this new order placed is a successor. And so if somebody receives that message, they will know that this one that has the embedded predecessor in it is the real one. That's the final result. And they will know what to do with that set. So that could be the way that you take care of things that you could possibly update. And now you could actually write a system that allows somebody to hit submit twice, because your web client is generating that hash. You can compute a hash in JavaScript. I used to think that was the crazy thing to do, but now, hey, it works. Just take that JSON object, hash it, and now you've got that order ID, and you've got that saved off before you even make the AJAX call in order to place the order. So while that's still going, if you change the cart and you hit submit twice, now you just embed that previous order and you send that whole thing off. So that takes care of the commutative property of a message with itself. And you're taking advantage of the fact that these things are immutable in order to do that. Now, immutable means they can't change. Well, here I'm changing something, I'm updating. but I'm doing so by creating a brand new message. Immutable also means you can't delete. What if I want to cancel an order? That's just another message. So order canceled is a message that has as its predecessor the order that you're canceling, and so that's going to be embedded within the order canceled. And that's going to mean that when it's received, those messages will be processed in the correct order. So these things, taken together, they give you the idempotent, commutative, and distributed properties. There is one more in our ACID 2.0. That's our distributed, or we just talked about distributed, the associative property. And so if you think about what you're really doing when you are collecting these messages, is you're doing a set union. This is the union of all of the messages that I've seen before. And so as long as you are doing that set union operation on immutable messages, then you're associative, you're commutative, you're idempotent, you're distributed. You are upholding the ACID 2.0 properties. And yeah, remember, these are properties that your application upholds so that it doesn't have to rely upon the database to give you the ACID 1.0 properties. As long as you group things together, no matter how you group them, you get the same results. You're associative. No matter how you order them, you get the same result. You're commutative. No matter how many times you do them, you get the same result. You're idempotent. No matter where you do them, you get the same result. You're distributed. That's your application doing that. And now the database doesn't have to be this magical, powerful, wonderful thing that does all this work for you. It can be nice and simple. It can scale. And you can take advantage of those benefits in your distributed system. So if you would like to learn a bit more about how you can use these properties, the properties of immutable messages and ACID 2.0 in order to create better distributed systems, I documented the whole system in The Art of Immutable Architecture. This book is going to come out in just 2 weeks. So you can sign up now at immutablearchitecture.com in order to get a newsletter. And I've been writing an issue every week with new information about how to build good, reliable distributed systems. And I will let you know exactly when you can order the book. So thank you very much. And I appreciate having the opportunity to come speak with you.
Well, thank you so much. I was going to ask you for where I can get more information, so perfect. This is really great. I really appreciate you doing this. It's good information, honestly. Really interesting take on like just the whole idea of not necessarily having ID and hashing the object, but I never thought you could do that. I've done it with other things in some ways, but never thought about just changing your ID in a way. How you do validation, or it's really cool. So thanks.
Yeah, cool. Thanks. And yeah, honestly, the idea of doing that is not unique to this system. You might be familiar with blockchain. A blockchain system computes the hash of a block and uses that as the identity now of that block. And that identity becomes the ID that the next one points back to in order to create the chain. It's just a linked list of immutable records. Cool stuff. Another system you might be familiar with that uses hashes in order to identify things. These things are commits. These things are changes to source code. Talking about Git. Every machine, every replica of your Git repository is going to compute those hashes in the same way, and that's why it uses a SHA as a hash.
Yeah, good point. I hadn't thought about that. Yep, that's awesome.
Yeah, I'd like to add that I really appreciate the practical examples, right? Certainly, you use math theory, but you apply that and create practical examples out of it, and so that's actually pretty impressive. I like that very much.
Cool. Yeah, I know that not everybody's going to read a math paper, but yeah, I get a kick out of them. So pouring through those things and then say, oh yeah, I can apply this. Oh, people need to know about this.
Right, good stuff. No, I'm sorry that we're distributed, so you won't hear a large round of applause, but you certainly deserve it.
Thank you. Thank you.
Yeah, there you go. We can do some. There you go. No, it's really good. I'm really glad it's recorded because I think I'm gonna have to watch it at least one more time to let it all kind of sink in.
Cool, cool. And another great resource, the resource that I first learned about ACID 2.0 from is patterns of distributed. Wait a minute. Oh goodness, I'll have to.
There is a book, Patterns of Distributed Architecture. There is.
Yeah, patterns of yeah. I think that's one. Basically, that that is talking about. Oh wait, no, it's reactive design patterns. That's the book I'm thinking of. So yeah, the Reactive Manifesto was of course everybody's got a manifesto. I'm going to have to write the Immutable Manifesto. But the Reactive Manifesto talks about how you can build a reliable distributed system by creating these architectures that follow reactive patterns that they are basically a functional program that computes the kind of a left fold of a bunch of events that occur throughout time. And that was the first time that I saw ACID 2.0, that if that computation that it does is associative, commutative, idempotent, and distributed, then all of those nodes will converge on the same answer. Basically, you'll be eventually consistent.
No, I think you should write the immutable architect or the immutable manifesto, because then you can be guaranteed it'll never be changed. So
that's
as good as my jokes get. Thank you all.
Michael, I had a
closing
question for you.
Yeah, here, question.
We just have the time. Just going back to your example of the order, placing the orders, how would you enforce a sort of a business level constraint where you didn't have the any data that was added that was relied upon, but you wanted a certain step to take place after another step just based on business rules? So, for example, you don't ship the package until the payment's been received.
Yeah. So this is a really simple diagram. Let's imagine that this one's a little bit closer to what we're talking about. So when you receive all these objects, these messages, in the book I call them facts. They're historical facts. Yeah, they each refer back to their predecessors, and so you're building up this directed acyclic graph of history. And so if you have a rule that says that I have to have I have to have my my payment before I ship it, or that sort of thing. Basically, what you're doing is you're writing a query that starts at some point in that graph, and then looks for leaves of a certain tree. So you're looking at the way things are structured, and you're looking at the types of messages. And you can imagine doing this in a network database, like a Neo4j kind of a database. And so if you can run that query and you come up with a certain set of results, now you know, okay, the rule has fired. So yeah, you come up with the results. Like one simple example is that as an accounting system, I'm going to create invoices for orders that have been placed. So we showed that as a queue or as a topic, and I'm pulling things off and I'm applying them one at a time. What I'm really doing is I'm querying for orders that have been placed that do not yet have invoices. So it's a query for one thing where the successor does not yet exist. So so you build up that kind of a query, and then anytime it returns a result, you know that you've got work to do. So that's a pattern that that kind of feeds the processing of those business rules. Yeah, that's getting into stuff in chapter 8. So it's getting kind of deep in there.
Thank you.
Any final questions, anyone? All right, Steve, you want to wrap it up?
Absolutely. All right, well, thank you, Michael. That was wonderful. The link for the SurveyMonkey survey has been posted in the chat. It is also available on the meetup page. So if you would like to leave some feedback from Michael, please do. Also, that is your way to get into the JetBrains raffle for the subscription. So I think that's all I have. Joe, anything else?
I just want to mention that for those of you who haven't been a part of our JetBrains raffle before, it is for any product that they offer, and that includes the full suite. So it's a pretty nice thing to win if you're interested in any of their tools. They do have a requirement that we register one of their giveaways at least every 3 months or 6 months. So the only thing we ask is that if you win it and you accept it, please make sure you install it and register it, because that'll keep them coming to us, and we can continue to give them away.
Absolutely. Okay, well, if there's no further questions, let's call it a meeting. Thank you, Michael. That was wonderful.
Very good. Thank you very much.
Yeah, thank you. Final applause. Good job.
Thank you.
Well done. Well done. Thank you.
All right. Enjoy your drive home.
Cheers.
Yeah, bye.